Hello everyone, my name is Sachin Kothari, and today I'll be presenting my second lab report, motion of a falling object. In our last lab report, we analyzed an object moving at a constant velocity in which we found that the net force is equal to 0. So, therefore, it would make this side of the equation 0, making the final equal to the initial, giving us a constant velocity. This time we're going to have two forces adding up to be our net force, and that is one of the goals of this lab, that the net force is now going to be non-zero. So, what is the weight force? The weight force is the force that pulls the object towards the Earth. It is equal to the mass of the object times the gravitational acceleration, which g is equal to 9.8 meters per second squared, times j hat, which is the direction that the object is falling in. Because the object is in free fall, it's going to fall downwards, and that's why we have a negative sign out front. The other type of force is a turbulent drag force. The drag force is the force that pulls the object away from the Earth. It is caused by the resistance of air. As the object falls, the air beneath it pushes on it and slows it down. The faster the object is falling, the more the drag force. In this lab, we were instructed to use turbulent drag in which the object's magnitude is proportional to the square of the object's speed. The general formula is this: b times the magnitude squared times v cap, or the direction. B is the drag coefficient. The drag coefficient is directly associated with the surface area of the object. The more the surface area, the more the drag. Let's look at tracker. So today, my system was a coffee filter. The coffee filter fell in the negative y direction. I didn't have to tilt my axis because the object fell in a straight line. From tracker, I obtained my initial position, my final y position, and my total time taken. I used this information and plugged it into tracker. My system was the coffee filter, and everything in my apartment was the surroundings. This was the negative y, this was the positive y-axis, this was the positive x, and this was the negative x. So we look at my first code with drag. I plugged in the mass. It was approximately 1 gram. So in kilograms, it was 0.00099 kilograms. We got the initial position from tracker. The initial velocity was 0 because the object was at rest in my hands. I set the delta t to be much less than the time step. G is equal to 9.8, which is the gravitational acceleration. J hat is the direction that the object is going to fall in and go in. B is our drag coefficient, and we had to find B through a method of trial and error, just like we were shown in the videos. And I found my number to be precisely this, and this number, even though it seems kind of small and weird, is actually the precise amount. And this value, when we run it, should give us a final position that's the final position on tracker. So I'll show you that when I run my code. So down here we have our weight force, which is the mass times g times j hat. We have the drag force, which is two magnitudes, indicating that's magnitude squared, times j hat, the direction, times our drag coefficient. These two add up to be our net force. We have Newton's second law, just like we did last time. The net force is going to be non-zero this time. This equation is our position update, and allows tracker to predict a new position every time. We're going to use arrows to represent the drag force and the weight force in this experiment, and I did it the same way we were showed in the videos, with 2 meters divided by mg, and I got my arrow scale to be 206.143. I'll run my code and let you see how it looks. So the yellow arrow represents the weight force, the blue arrow represents the drag force, and the object falls in the negative y direction. So this value here is negative 2.285, and that's the final position that we see here in tracker. And that means my B constant drag coefficient is correct. So now let's examine the same code with no drag, only the effect of gravity. The only thing different here, everything is the same, we just take off the drag force. So the drag force is gone, and the F net is equal to gravity, and if you run this, it's just going to fall in a straight line. This yellow represents the weight force, and the object just falls, and it's going to run off the page here too. Now let's, I haven't talked about the graphs yet, so I'm just going to put them all in one and talk about them. So part A was the experimental, part B was the model position with no drag, and part C was the model position with drag. So if you notice that the experimental and the model position with drag are basically the same line, meaning the experiment was pretty successful. This one has a higher velocity, it falls faster. This one has a lower velocity, and it falls slower. Now let's answer the questions, because that kind of tells you more about the graph. Is there a terminal velocity? Yes, there is a terminal velocity. How do we know that? Because these lines are linear. Terminal velocity is when the weight force and the drag force cancel each other out, giving you a net force of 0, meaning a terminal velocity equals a constant velocity. So the second question asks, what if the object was thrown down with initial velocity? Would terminal velocity be reached earlier at the same time or different? So let's see what happens, and the best way to do this is I changed the graphs to represent the velocity rather than the position down here. And up here I kept the velocity to be 0, and here in this one I kept the velocity to be negative 10, since it's being thrown downwards. Now let's look at both of the graphs and see how they compare to one another. So what we see is that both of these literally line up and they're the exact same. What does that mean? That means terminal velocity is going to be reached at the exact same time. It does not matter